Hello, let's go to this third video of the mathematical analysis where we can go deep in the knowledge of numbers and now in the third topic numerical sequence and series, right? The first topic is convergent sequence. A sequence Pn in a metric space X is said to converge if there is a point P belongs to X with the following property. For every epsilon greater than 0, there is an integer n such that small n is, is bigger than n implies that the distance between Pn and P is smaller than epsilon. In this case, we also say that Pn converges to P, or that P is the limit of Pn. And you write Pn approaches P, or using the notation of limit of n as n goes to limit of Pn as n goes to infinity is equals to P. If the sequence of Pn does not converge, it's said to diverge. It might be well to point out that our definition of convergent of sequence depends not only on Pn but also on X. This is very important, right guys? Because we are here to see the mathematical analysis, not to become a mathematician, but to use the concepts of mathematics to understand what happened in a computer. And this second topic here is really important because the majority of books, at least written in West, in Europe, in the United States, and of course in Brazil, when you say something about a numerical procedure, we realize that all the rules are written in a real number, of course, in X, in a metric space X. And you try to implement that code in a computer, and what happened? In that computer, you don't have the same space of the rules. So it doesn't mean that it is going to converge in a computer. It's more precise to say convergent in X. The set of all points Pn, when n is going to 1, 2, 3, and so on, is the range of Pn. The sequence Pn is said to be bounded if its range is bounded as well. So here is another way to, it's just an example. When you have Sn equals 1 divided by n, then we get the limit here, of course it's going to 0. If S belongs to the real numbers, so if Sn equals to the square of n, the sequence Sn is unbounded. In the example S, if S now of course is Sn equals to 1, a constant number, so this sequence is converged to 1, is bounded, and has a finite range. The theorem 2 is going to be mixture some concepts, but it's not so difficult, I suppose. Pn converges to P belongs to X if and only if every neighborhood of P contains all but finitely many of the terms of Pn. So in the neighborhood contains a huge, of course, infinite terms of Pn. If P belongs to X, so another P belongs to X, if the sequence Pn converges to P and slash P, then slash P is equal P, right? If Pn converges, then the sequence Pn is bounded. If E contains X and if P is limit point of E, then there is a sequence Pn in E such that P equals the limit of Pn when n goes to infinity. Suppose Sn in T, you can make a complex sequence, mix the numbers, so the addition of these two sequences equals the sum of the results. You can do the same thing for multiply a constant make some multiplication of these two sequences, and when you get the division as well. Subsequence. Subsequence is not so difficult because if you get a subsequence of the number, you are going to have the same result as well. If Pn, the theorem 14, if Pn is a sequence in a compact vector space X, then some subsequence Pn converges to a point of X. Every bounded sequence ERQ contains a convergent subsequence. The subsequential limits of a subsequence Pn in a metric space X form a closed subset of X. This is another important point. This is perhaps one of the most important definitions in the mathematical analysis, in my opinion, to study in computer arithmetics. A sequence Pn in a metric is a metric space X is said to be a Cauchy sequence if, for every epsilon greater than 0, there is an integer n such that the distance between Pn and Pm is lower than epsilon if n, small n, is greater than n and m, for Mary, is greater than n here. This is the French mathematician, one of the first guys, at least in West, that start to study mathematical analysis. So the diameter, it's another way to put almost the same thing, because the diameter is the distance between P and Q. If this diameter it's going to become smaller and smaller, of course in some point you are going to get the number, right? And you can take a look at this in a sort of closure of set, because if diameter of slash e here is the same of diameter of e, and you can make the compact sets in the same way as well. In any metric space X, every convergent sequence is a Cauchy sequence. If X is a compact metric space, and if Pn is a Cauchy sequence X, then Pn converges to some point X as well. A sequence converges in RQ if and only if a Cauchy sequence is usually called the Cauchy criterion for convergence. This definition called 2 here, you can get monotonically or increase or monotonic decrease. It's very important to see the behavior of some convergence sequence. Suppose Sn is monotonic, right? So in this situation, then Sn converges if and only if it's bounded. If Sn be a sequence of real numbers with the following property: for every real m, for Mary, there is an integer n such that small n is greater than n, implies Sn is greater than m. So we can write Sn approach plus infinity. Let Sn in definition 44 here is the same thing that you are going to use, but when you use the extended number. So instead of going to something, you can use plus infinity and minus infinity, but it's not precise an addition of what you have said up to now. We can also write definition 14, that y that I said, so we can go to supremo of Sn. It's S star here above and S star here below. Some special sequence, it's quite very common here to study is in basic calculus number. If p is greater than 0, then the limit of this equation here goes to 0. If p greater than 0, this limit is going to 1. And all these, there are many of this sequence. It's quite easy to go to any Wikipedia page to see very many special sequences. Give a sequence an, you use the notation the summation of some numbers, some terms of this sequence, np, n equals to p, to q, p lower than q, to denotate the sum of all the numbers ap, p1, p2 up to aq, with an we associate a sequence Sn, where Sn is a partial result of this. For Sn, you also use the symbolic expression A1 plus A2, so on. More concisely, we can make a summation of all terms An. The symbol in 33 here we call the infinite series, or just a series. The number Sn are called the partial sums of series. If Sn converges to S, you say that the series converges, and you write the equation 21. S is the limit of a sequence of sums. It's not obtained simply by addition. If the sequence n diverges, the series is said to diverge. Every theorem about sequence can be stated in terms of series, right? It's quite tricky here. One of perhaps results, of course, it's a weak result, I would say, but if you are curious about some trick mathematics, you can find some very curiosity about the sequence, the sum of the sequence 1 plus 2 plus 3 plus 4 and so on. There are some tricks that you can get minus 1 divided by 12. It's quite tricky, but it's at least interesting to apply some weak concepts of mathematics, right? The Cauchy criteria can be stated as the following theorem. Theorem 19, the sum of An converges if and only if for every epsilon greater than 0 there is an integral n such that if you sum of these numbers you are going to have some smaller than e. You can choose m and a. What is going to on here, of course? To converge the sum, some terms of n is going to be 0, or at least is going to approach 0. If the sum of n converges, then you can write the number here is to go 0. It's what I have said. It's a consequence of the equation 22. The theorem 21, a series of non-negative terms converge if and only if its partial sums form a bounded sequence. And this is a comparison test. That's a way to see if you can get as well this kind of result. And perhaps one of the most famous series is the geometric series. If 0 is smaller than x is smaller than 1, then if you get the summation x1 here, you are going to get 1 divided by 1 by minus x. In the next slides you can see the proof. I'm not going through because it's quite basic, but if you have some doubts you can ask me in your meeting, right? The root and ratio tests, you can use that to see if some sequence converge. So the root, you can get some tests here to see if alpha is smaller than 1, so you are going to converge, otherwise diverge. If alpha equals 1, the test gives no information. You can do the ratio test as well. It's quite useful because if you can get some sort of generalization of n terms, if these n terms has n approach to infinity, if you divide the an plus 1 term divided by an term, if you get smaller than 1, so the set diverges, otherwise diverges, right? The limits of function. It is another way to see that the connection between limits and functions. So you can write equations 25, 26 and 27. It's another way to write that. If you that the definition 47, it's not so new, it's not so old, it's not so old. It's called the epsilon delta limit definition. It's given by Bernard Bolzan in 1817. Its modern version due to Carl Weierstrass. It's written a couple of years later, perhaps some decades, And definition 47 it's written like that. The function f approaches the limit L near C means for every epsilon there is some delta greater than 0 such that for all x 0 is lower than the norm of x minus c is smaller than delta. Then the difference between fx minus L, the absolute value of that difference, is lower than epsilon. You can write the definition 47 in the equation 28. Graphically, it's much more easy to perhaps to understand. If you get a number x close to c by the difference of delta, if you apply some functions here, we are going to get L, right? L with the difference between epsilon. But the limit says that you can decrease here epsilon. You are going to find delta as small as possible to see this function. And here I'd like to ask you to realize what's going to happen in an iterate of a function if you are using a computer. When you are using a computer, of course, you cannot sometimes, perhaps the majority of the times, you cannot get a number c. You are going to get some approximations. If you apply this function f, you are going to get some approximations of L's as well. If this result is applied and again, you can get some distance very big of the final result. Theorem 24 is just to say that if you have definition 46, then when x approaches p, it's the same that n the second of Pn, right? So it's a sort of to make a mixture between limit of the definition and the sequence. Suppose A contains x, a metric space P is a limit point, so you can get this combination of the sum of the functions and the sum of the results as well. Continuous functions is a consequence if you have the definition 48 holds for every x and y belongs for this definition, right? And the composition of functions, it's quite important because what happened in a iterate of a map, for example a chaotic map that you are going to study, if of course the composition of a function. And continued compactness, if a map F you have it's bounded, so when you apply the F you can get the same support, so the same consequence for theorem 27. Suppose F is a continuous map of compact matrix space X, then the function X is compacted as well, right? So it's going to be important. The conclusion may also be stated as follows. There exists point P and Q that if you apply the function you can get the consequence of the compactness as well. The uniform continuous, it means that you can get epsilon and delta, and if you apply functions in P and Q you can get this uniform continuity as well, right? The theorem 29, let F be a continuous map on compact matrix space X into a matrix space Y, then F is uniformly continuous on X. Continuity and connectedness. The intermediate value theorem, perhaps it's quite important to see some continuous function, what it states. If you have an interval in B, A, B, if f of A is lower than f of B, and f and C is a number such that fa is lower than C is lower than fb, then there exists a point A in the interval, sorry, exists a point X belongs to this interval such that fx equals to c. You don't have this in a computer, of course. So this is you can use that to see what's going on wrong when you are going to do some computer simulations. Discontinuities, I'm not going to go further here because discontinuity is quite a mathematical analysis. So, but you can see that some discontinuities can happen when you are going to use some computer simulations. Monotonic functions, it's quite easy to understand because when you get monotonic increase, if you have a louder than x, louder than y, louder than b, it implies that f of x is louder than f of y. You can say like that if you see the limit in the right or in the left of x plus x minus, so you can have the same results. Infinite limits and infinity, when you use that to extend the previous notions for the real extent. So it's quite a consequence of what you have said up to now. Three important theorems. I'd like to stand that because you are going to use to see what's going to happen in the logistic map when you are doing some computer simulations. If f is continuous on a and b, f of a is louder than 0 is louder than fb. So there is some x in this interval such that fx equals to 0. If f is continuous in b, then f is bounded above. Right, but pay attention to that, If f is continuous b, then f is bounded above. The composition of a function of a continuous function is also continuous. So the composition of a function is bounded above as well. What you are going to do when you are using a map, an iterative map, you are going to make a composition of a function. So it's bounded. But sometimes when you are going to make some computer simulation of the logistic map, they say that diverge in a computer. It's not what said here in the theorem 34, right? If f is continuous, then there's some number in this interval that you can make this definition of the theorem 35. The derivative, just the definition of derivative. Theorem 36, it's just to say what is a differentiated point. You can make some combination of these functions in theorem 37 and theorem 5.5, just to say that the composition of a function, you can make these derivatives as well, right? And you can use this derivative to produce the result when you don't have as in 39. In definition for 57, you can make the use of derivative to get the maximum of a number, and let f define on b. If it has local maximal, it says that there is some derivative of this number equals 0. It's very useful to make some optimization problem, use gradient and derivative function as well, right? And suppose f and g are real and differentiable, so you can use this to make some suppositions and to get, most of all, when you get this result, so it's the same to the result of derivative, it's the same as the function as well, right? So when you have a differentiation, you can make this differentiation so on, so on, when the function is continuous. And here, just to say that you can use this as a Taylor sequence, and it's very useful to calculate some functions, because in a computer you don't have means to calculate the e to x or the trigonometric functions as sin of x. And here you are not going to make this exercise in this point, just the end of the course, but I'd like to see to use three important theorems to reflect on simulation results of the logistic map with bifurcation parameter in the range 0 is lower than a is lower than 5. Usually we think about the logistic map up to 4, and here I'd like to ask you to think about when a is greater than 4. You like to see to realize some points in this my paper, so please go through, and you also going to take a look in the paper written by May from 1976, right? It's advanced topics in the end of the course. You can do this exercise here in terms of 3 and 4, as I have said before. Okay, so I'd like to say again thank you for be patient to see my videos, and I hope that I can bring some novelty and some knowledge for you.